Need to regulate something? In 99% of cases, all you need is a PID regulator or several PID regulators. In this video, I'm going to break down how a PID regulator works and what I hope is an easy to understand way. This video is a part of a larger series about the PID regulator. In this series, I'm covering how it works, when you should use it, when you should not use it, and how to dial it in, among other things. Those videos will be in the description if they're out. So, if you've worked in automation at all or with any sort of control, I'm sure you've run into the PID regulator. It's the most well-used regulator in the world, and that is for good reason. It's relatively simple and easy to understand, and its applications are huge. You can use it for so many different things. So let me break it down for you. Let's do the car example. You want to use the on-off strategy for controlling this car. And essentially what this means is that you're trying to keep a speed of 70 kilometers per hour. Let's say you're below the speed. You're at 65 or something like this. What you would do in an on-off regulator is you would press the gas pedal as far down as you can. You would overshoot here, right? And as soon as you get over 70 kilometers per hour, you would release the pedal. And you would do this over and over again. This is a way to drive a car for sure. You will be around 70 kilometers per hour, but it's not very smooth, and I don't think you would like it. And for many processes, it is not very optimal either. And this is kind of what the PID regulator solves, right? Specifically the P part, or PID regulator. Before we dive into the PID regulator and how it works, let's do a little crash course on regulators and the different terms I will be using in this video. A regulator is something that controls something, right? It controls a process. I will talk a lot about the control of a speedometer or the speed of a car in this video. And you usually draw it like this. You have a process, and then you have a regulator. Then from the regulator there is a control signal. From the process there is a measured signal, Y. There is a reference value, and then there's a reference value. Then we have the error, which is equal to the control signal minus the reference signal. And it's designated with an E here if that's not clear. I'm going to be talking a lot about a car example, as I mentioned previously. And to illustrate, if you're driving a car and you want to keep it at 70 kilometers per hour and you're acting as the regulator, then R would be 70 kilometers per hour. That's your reference, that's what you're trying to drive at. The control signal would be how hard am I pushing on the pedal. Let's say you're pushing at 50%. Something like that. We say, 0.5. 50% push on the pedal. And then Y is the actual speed you're driving at, maybe 65 kilometers per hour. This moment. So this is the basics that you need to understand to be able to follow this. And yes, let me add that the error in this case would be -5 kilometers per hour. Okay, so a PID regulator, it has 3 parts. It has the P, I, and D parts, which are the proportional, the integral, and the derivative parts. And they all aim to solve different problems. I like to think about these things, or these parts, as the now and the past and the future. Why will become apparent, but let's start with the first part now, the P part. Instead of completely releasing the gas pedal or completely pressing down the gas pedal, you adjust it in proportion to how far you are away from your target speed, in this case, 70 kilometers per hour. It's usually drawn on a graph, something like this. Where this here is the control signal, and this is the error, E. And this would be U max and U min. So this is great, because by adjusting this in proportion to how far you get, you're not going to get any of these oscillations anymore. You'll get eventually to a constant speed. The formula for this looks like the following. You have U and U0, which is this value here, plus Ke, which is the strength of the P part, is between some error values here that you decide. And here we have U max, U min. So essentially, when you're in between these 2 points, you adjust it in proportion. Now, there's one issue with this regulator. It works really good. You get a smooth experience. You reach a desired speed where you stay comfortably and there are no oscillations. But there's one problem, and it's a little bit hard to explain, and you kind of need to do a more mathematical explanation to get there. But I will try my best to lay it out for you. The problem is that the P regulator, it kind of gives up. It doesn't stop when you have reached the desired speed. You adjust in proportion until you get to a point where you have a stable speed. When you have a stable speed, then the P part of the regulator, it gives up, it's satisfied. I'm at 65, I wanted to get to 70, but at least it's a smooth experience here at 65, so I'm gonna stay here. That's how the P regulator operates. But we don't want to be at 65, we want to be at 70, and that's why we have to look at the integral part as well. And that's why we add the integral part. Integral part, it's looking at the past. Am I getting anywhere? Okay? Let's write out the formula for it, and I will talk a little bit around that. Here, we have replaced this part with an integral formula, or an integration of the error over time. So we have U, and it's still K, but then we have the integral 1 divided by the integral time over an integral from the error plus C. So there's 2 parts here now. We still have the P part here, but now we also have the I part. And let's look at this, because this is integrating the error, right? So what would happen, the way I'm going to explain this is to look at the scenario where we get to 65 kilometers per hour. Or we get to a stable point. So let's say we want to reach this speed, 70 kilometers per hour. The regulator has gotten us up here, to 65. And we're stuck here with the P. But the I regulator, it integrates this error, the area here, right? So as soon as this area is not 0, it will grow. So it will push up till it reaches 70. and the area stops growing, that's the only time it gives up. So I like to think about it like this. The I part, it never gives up till you reach your set point. It never gives up. The P point, it gives up. The P regulator, it gives up when you reach the smooth speed. And the I regulator, it never gives up till you reached the right speed. And at this point, we've talked about the P regulator, we've talked about the I regulator, and those are the most important parts. 95% of the time out there, you only need these two parts and it will be a fine regulator and it will do the job you want it to do just perfectly fine. And you don't have to worry about it. But there is an additional part, and it is the D part that we've talked about. And as I said, the D part, it's the future. The future. So let's look at this. Let's look at a graph. So let's study these two graphs. Here, let's imagine that the I part is the same. So the integral part is the same in these two. Therefore, we have the same integral action. Then let's look at the P parts. And we imagine that the P parts, they're also the same. So we have the same now. But you and me, we can clearly see that these two, they're quite different. In this graph here, the error is getting smaller. We're heading in the right direction. And we would like to just continue like we're doing, nice and slow, and go down till we have zero error. We would know that. And in this one, all of a sudden the error is starting to increase. And because of the error increasing, we would like to push a little harder on the control signal. This here is what's taken into account with the D part, with the derivative part. What direction are we going in? And I think the easiest way of thinking about this is heating up something. Like usually temperature problems and heating is where this is important, right? Let's imagine we're heating up a thick cast iron pan on the stove. At some point, you will know that you can turn off the stove and it will still continue heating. You know that the temperature is heading up, and then predictively you can turn down the control signal to predict. You're predicting the future. You're predicting that it will continue going up so I can ease off of the control action. This is what a derivative part is. And I'll write down the formula for it. Actually, I will not, because I don't want to overcomplicate things. But that's essentially it. We're looking into when and the parameter. So essentially, these 3 parameters are what you can change to make these different parts stronger. You want a stronger proportional part, you change K, Ti for integral, Td for derivative, and so on and so forth. But we'll talk more about dialing these parameters in a different video. There are many different ways of doing it. You can do it experimentally, or you can calculate what these should be optimally. Usually you have to do a mix of the two. A PID has 3 parts: the proportional, the integral, and the derivative. We can think about these as the present, the past, and the future. A PI regulator is enough for almost all use cases, or many of them, most that you're going to run into. The P part makes sure that we don't get these oscillations that we get with the on-off controller, and the I part makes sure that we actually reach the temperature we want. And the D part is a little extra flavor, a little extra oomph to make sure that the regulator is good at reaching the speed, reaching the desired target. It's an improvement, but it's not a necessity. It's usually good to use in heating applications. And PID regulators, they work very well for linear systems, where there's a clear connection between the control system and the control signal and the measured signal. It doesn't work as well for a linear system, so we'll talk more about that in another video. I hope you feel like you have some insight into a PID regulator and you got a good grip on what it is now. In the next video, we're going to talk about when you would use a PID regulator and when you would not. Then after that, we're going to have a video about dialing in these 3 parameters we've talked about in this video. And then we'll extend with more videos about other regulators and also more features you can add to the PID. Thank you for watching. The links to all these videos, if they're out, will be in the description. See you in the next video.